Okay, so um, today we're starting representation theory of finite groups. And so this is really the study of how finite groups can act by symmetries of vector spaces. So you can represent the object in terms of symmetries. So you can represent a group in terms of symmetries. So and we already did this in one way. So the theory of group actions, or G sets. This was the theory of groups acting on sets. And so the G set was just and this was set X and a map from G to automorphisms of X. It's a group homomorphism from G to automorphisms of X. Okay, and while we saw there's sort of basic structure theory for G sets. In every G set was a disjoint unit of orbits. And then each orbit is isomorphic to G mod the stabilizer of X for any X in the orbit. So every G set decomposed uniquely into these simple irreducible chunks, and where you have an orbit, and so then these orbits all had this canonical form. It was G mod some subgroup. Different subgroups, so conjugate subgroups give the same G set up to isomorphism, but that's fine. I mean, there's some specific building blocks, and then everything else is just getting made from a disjoint union of those building blocks. Okay, and so I mean, this is the theory we're going to emulate and talk about today, but for representations. So group representation. So it's a map from G, a group, to V, which we call this rho, where V is now a vector space. So V is a vector space over a field K. So, okay, so sometimes we call automorphisms of V, we write it the general linear group of V. So this is like, GLN is the vector space automorphisms of K to the N. And so this is just a generalization notation where you don't fix a basis for your vector space. I mean, sometimes we write, when we're talking about group representations, sometimes we write rho. Sometimes we write just V. Sometimes we write the pair. So I'm just saying whatever's convenient. So there are certain constructions where, like, for example, you can take the tensor product of two representations. And so it's convenient to just write that as a tensor product of vector spaces, and the operation on the representation is implicit. And similarly for some other operations. And when other times you really want to emphasize that you have an actual map rho. Okay, and so anyway, that's what a group representation is. So in particular, a group representation is an action on a set, because if you're a vector space automorphism, you're in particular an automorphism of this vector of the vector space just thought of as a set. And of course, this decomposition into orbits is not going to be so useful typically. Like if K is an infinite field and sort of this is like a finite dimensional vector space, and you're still going to have sort of infinitely many points, and sort of G is a finite group, then so you'll have sort of infinitely many orbits. So and somehow that's not the right way to think of it. So even though this is sort of in particular a G set, that won't be sort of a useful way to think of it. Though there will be a useful relation with G sets. Okay, so that's what a group representation is. And let me fill in a few related concepts. So a map of representations. So phi from V1, let's say row 1 V1 to row 2 V2 is a map of vector spaces so a linear map of vector spaces such that it commutes with the G action. So and you can write this as if I take phi and I apply sort of row 1 of G first, then that's the same as sort of applying row 2 of G after applying phi. So for all G V. I mean, another way to write this is, so this is if and only if say this way, so phi composed with row 1 of G composed with row 2 of G, row 1 of G inverse composed with row 2 of G is equal to phi. So, and you can sort of think of it as you're acting sort of, G is acting on this map between these two vector spaces. So, and this is if and only if phi is actually an element that's fixed for the natural action of G on sort of all vector space homomorphisms from V1 to V2. So when I put this superscript here, this means sort of G invariance for the action on this set. When this is the representation, in fact, but it's an action on the set. So here, I mean, this formula is telling you what the action is. So the action is sort of by conjugation. So you pre-compose of row 1 inverse and these row 1 of G inverse, and you post-compose of row 2 of G. Another way to think about this action, I mean, so this is this identification, and there's a canonical identification of vector spaces of sort of the linear maps from V1 to V2 is V1 dual tensor V2. And that sort of has an action. There's an action on sort of the dual V1. So it's sort of given by pre-composition with row 1 of G inverse. And you can sort of, if you follow your nose, you can sort of write down exactly what this is. And then there's an action on this tensor product. So you just act on each factor in the tensor product. And this space has sort of a natural G action, which is or agrees with the natural G action here. And so you can write this either way. And the point is sort of saying you have a map of G representations is the same as saying you have sort of a map of vector spaces that's invariant under the natural G action, which is equivalent to saying sort of the G action sort of commutes with phi. And so it's the same thing. I mean, this is the same thing it would meant to have a map of G sets. We didn't talk too much about maps of G sets, but if you wrote down the definition of map of G set, you could sort of literally just replace the word vector space with the word set everywhere, and sort of you would, maybe you wouldn't have this dual thing, but you sort of have something like this. But anyway, okay, so that's what I wanted to say. And well, I've told you what a G representation, a group representation of G is, and I've told you what a map of between two representations of G is, and so that means sort of I have a category of representations of G. So it's like a place where I can do mathematics. And so we want to study that category. And so we want to like understand like what are its building blocks, just sort of like we studied the category of groups and sort of saw like simple groups, or like the category of finite groups, like simple groups are the building blocks. Like the category of modules, sort of we studied like, for a fixed principal ideal domain, we studied the category of modules of a PID. Or like for a fixed group G, we studied the category of G sets. Like now for a fixed group G, we want to understand sort of its category of representations. I mean, why do we want to do that? Well, I mean, several reasons. I mean, for one, it turns out, so, and if you look at Dummett and Foote, for example, we'll put a lot of emphasis on this. This is not something I'm going to put so much emphasis on, but I mean, thinking about the representations a group has is an incredibly useful way to understand that group. I mean, somehow, yeah, I mean, you've been thinking about, and just in the same way that like thinking about G sets was sort of crucial to proving the Seeloff theorems. Thinking about group representation sort of gives you another way to sort of understand groups through their symmetries and sort of through the way they act on sort of more concrete objects, and you can use that to sort of study the structure of groups. For example, like to prove Burnside's theorem. So, I mean, it's useful just from like the aspect of internal group theory. And I think, I mean, that's a good perspective if you're going to be a group theorist. Probably most of us are not group theorists. And so I think it's better to sort of think about more in the opposite direction, which is, I mean, it gives you a real, I mean, you often are in a situation where you have a group acting, or like even if you didn't realize you have a group acting, you have a group acting. And this sort of, if you can understand very well the structure of sort of groups acting on vector spaces, then you can use that structure in profitable ways. So there's like one really elementary example of this is, so if you look at sort of these different notions of curvature that show up in Riemannian geometry, like so these different curvature tensors you get, I mean, they come, like one way to understand sort of where these different notions of curvature are coming from is sort of, well, you have sort of one sort of essential notion, and then you sort of break up that essential notion according to like an action of the symmetric group. So, and so like this curvature is living in some space of tensors, and that space of tensors has an action of the symmetric group sort of by permuting the tensor entries. And then sort of if you break up according to the irreducible representations of that symmetric group, you get sort of these different sort of classical notions of curvature. That sort of explains why these notions are distinguished. I mean, and things like this come up all the time. An example that's relevant for us is, I mean, the Galois group acts on, like if you have a Galois group that acts on, so you have L over K as a field, a Galois extension, so then the Galois group acts on L, and well, it acts on L as a field, but in particular, that means it acts on L as a K vector space. So sort of L, like a field extension is actually sort of a representation of that Galois group on the vector space over K, so over the base field. So if somehow if you understand it as a representation, that can sort of help you understand sort of, well, arithmetic properties of that field extension. And it turns out, like, it ends up having a really nice description as a representation. So like at least if Galois extension characteristic 0, then there's something called the normal basis theorem that tells you sort of it's actually always the regular representation. So I'll sort of say what the regular representation is in a minute, but this is a very simple representation to understand. And using that, like, you can prove interesting things. So for example, on your homework this week, you have a problem. So, well, first you have a problem to prove that, and then you have a problem to sort of prove this converse direction in Kummer theory that we talked about in the problem session today. So we talked about how, like, if you have a field that has the nth roots of unity and you have a z mod nz extension, then you can really get that extension by extracting an nth root. And so, yeah, we'll use representation theory to prove that. So, and somehow this is the perspective I prefer on representation theory. It's that not that you want to sort of study representation so you understand the group. It's that like sort of finite group actions in particular sort of just show up in structures all over mathematics. And if you have sort of a good sort of basic understanding of like how those break down, then sort of this gives you a really useful way of organizing ideas. Just as one more example, like to throw one more example out there, like you can use this to understand like card shuffling. I mean, so representation theory is like how you can get sort of good estimates about like how efficient card shuffling is. Okay, so anyway, so this is the perspective we'll sort of approach. Okay, bring this with, and so let me make a definition. So we want to sort of study building blocks of representations, and so we should sort of know what we mean. So a representation B is irreducible if it's only sub-representations are sort of, well, the zero representation and itself. So AV. And so what is a sub-representation? Well, it's just a subspace that's preserved by the group action. So this is okay. So now let me say the main theorem. So okay, so irreducible representations are going to be the building blocks. I mean, that's not surprising from the definition. I mean, irreducible, and like this definition makes sense sort of in like many different categories. I mean, this makes sense sort of in the category of rings, or like or in the category of modules, for example. Like if you have fix a ring, you look at modules of that ring. So it makes sense to sort of say a module is irreducible if and only if it's only sort of sub-representations are zero in itself. Okay, and this is something you guys may or may not have talked about very much last term. And and so the rings are kind of, so we're used to seeing this is not always such a useful notion, but in this category, it will be a very useful notion. And like this notion also exists in the category of G sets, and so the irreducible things were just sort of the transitive G sets. So of course, one to like having an orbit. Okay, so let's look at an example. So if X is a G set, then we write K brackets X. So this is just equal to sort of the K vector space with basis X. So I just treat sort of the elements of X as sort of formal symbols, and then I take sort of formal linear combinations. So an element here looks like sum of AI X, sum over all X, A sub X times X, over all X and X. And if X is an infinite, and you should think X is a finite set. If X is an infinite set, this still makes sense, and I can just take, well, then there's some choice about whether you want to take infinite formal sums or finite formal sums, and I would, with this notation, I would take finite formal sums. Okay, but then just, well, let me even say X is a finite G set, and G is a finite group. Okay, I mean, everything I've said so far sort of makes sense for an arbitrary group, but soon G will always be finite. So, so you can take G to be a finite group in your head anytime you want. Okay, so we have this vector space, and then sort of the action is just given by sort of G of X, G calculate this way, and G times sum of. And you just sort of, it's just induced by the action on the set. So this is, you just pull in the action. And you just act on the elements, just like you would on the set. I mean, you can think about this different ways. If you want, you could think about this as sort of an action. A very natural way to think about this is sort of, this is the set of like distributions on functions on sort of k-valued functions on this set, and then sort of x is the Dirac distribution, and then this is sort of a very natural way to write this down. But you can also just think of it as being formal symbols. Okay, so this is a G set, and so claim, and if x is not equal to just a single point, then this is not irreducible. And of course, if it's a point, then it's a one-dimensional vector space. It's sort of irreducible as a vector space. In a one-dimensional vector space, any subspace is either a zero space or the whole thing. So then sort of as a representation, it also has to be irreducible. Okay, and I'm saying if you take a G set, like even if you take sort of like a transitive G set, so something that's sort of irreducible as a G set, the space of functions on it is not irreducible if it sort of had more than one element in it. And the reason is, if I look at just the span of the element where I just sort of add up all the elements in X, then this is an invariant subspace. This is a subrepresentation. So you always have sort of this one-dimensional subrepresentation. And so the action of G on this subrepresentation is trivial. So on this line. Because, I mean, like if you hit this with an element of G, that just sort of permutes elements of X, but sort of since you're summing up all of the elements of X, like you land on the same thing. And in fact, I mean, sort of not only is the action of G trivial on this line, like this really is sort of, this is the set of G invariants. So everything that's invariant, it's not so hard to check, sort of lies in this line. So it's some scalar multiple of this element. And the point is, if you're invariant on the action of G, you can just, sorry, this is if X is a transitive G set. And so if X is not a transitive G set, then this is not true. And then there's sort of the invariants are sort of sums of things that are constant on orbits. But okay, so good. This is sort of an interesting feature, though. I mean, somehow this is telling you that in the information you got by looking at a group action is somehow refined in looking at the sort of corresponding representation, because even though sort of a transitive G set is irreducible as sort of a G set, it's not, and it's not like this representation you built out of it is not irreducible unless you start with a trivial G set. Okay, so this is sort of some interesting example. Let me say another one. So one-dimensional representations are just characters. In the sense of week 6. So the point is sort of, if V is one-dimensional, then GLV is sort of canonically isomorphic to K cross. I mean, if V is one-dimensional, that means every linear transformation is just multiplication by some element of K. So the invertible ones are just multiplication by elements of K cross. And so then sort of a character, any one-dimensional representation. So rho is just a map from G to K cross if V is one-dimensional. Right, so one-dimensional representations are just characters in the sense they're sort of homomorphisms from G to K cross. Let me just highlight, and I mentioned this back at the time, and I'll mention it again now because the meaning of this word is about to change. So oops. So I'm going to start talking next time about the character of a representation. And sort of when, for one-dimensional representations, the character will be equivalent to the representation, but somehow it'll always be equivalent, but in the cases we talk about, but in one-dimensional case, it'll literally be the same. In a two-dimensional, like in a higher dimensional case, so it'll be sort of extracting some information from the group homomorphism that sort of ends up to be a really convenient way to encode it. Okay. Good. So those were some examples. And then, oh, sorry, and one-dimensional representations are sort of characters, and they are irreducible. And again, just because sort of they're already irreducible, like in the category of vector spaces, there's just every subspace is either the zero subspace or the whole thing. Okay. But of course, there are higher, and there are other, and what we'll see is sort of for non-abelian groups, there are other irreducible representations. So there are sort of higher dimensional irreps. So irrep is short for irreducible representations. So yeah, so here's an example. So if I take S3 acting on so set 1, 2, 3, then so this permutation representation construction, so the thing where I take sort of a set and I sort of take K brackets X, just gives you sort of the action of S3 on K3, where S3 is just by permutation of coordinates. So this is a action on three-dimensional vector space. This is not irreducible because sort of not irreducible. I mean, we already saw sort of E1 plus E2 plus E3 is as a subspace. But in fact, well, yeah, let me be lazy. Let me not say, let me take K to just be the complex numbers here. So spoiler, representation theory is nicer in characteristic 0 and over an algebraically closed field. And there's lots of interesting things outside those cases, but like the nicest behavior is in this case. So we'll do more in this case than in any other case. Okay, so this is a subspace, and so this line is a subspace of this C3 representation, and this line is as a sub-representation, sorry. Again, we abbreviate that as subrep. But that's a one-dimensional sub-representation, sort of, it gives you the trivial character. So the trivial character is just sort of the homomorphism that sends S3 just to the identity element. So it's going to be a trivial character, but it turns out, so the subspace actually has a complement. So if I look at AE1 plus BE2 plus CE3, if I look at the subspace of these elements such that A plus B plus C is equal to 0, then that's definitely preserved by, well, and this is a subspace, and it's definitely preserved by permuting the variable or permuting the coordinates. And this is a two-dimensional irreducible subspace. So we'll introduce some tools that make this very easy to check starting next time. For now, and if you want to check this, you can easily check this by hand. I mean, you can sort of take any vector and sort of just hit, like take a non-zero vector in here and then just hit it with sort of an element of S3 and sort of so that you get sort of something linearly independent. So, well, this is a two-dimensional subspace, so you just need to get sort of two linearly independent vectors. Yeah, well, anyway, you can think about this, but this is really irreducible. And this is sort of not like unusual. This is sort of what you expect. I mean, for non-abelian groups, you always have, and this is a characterization of non-abelian groups actually. So a non-abelian group always, a finite non-abelian group always has sort of a irreducible representation, an irreducible representation of dimension larger than 1. Okay, so good. Okay, so yeah, so let me get to the big classification theorem. So this is the thing that makes everything work. So if G is a group, so if G is a finite group, and the characteristic of K is coprime to the order of G, then any finite dimensional, so there's a whole theory of infinite dimensional representations. It's not so, it doesn't matter for finite groups, but well, okay, anyway. We'll always be talking about finite groups and finite dimensional representations. So a finite dimensional representation of G on a K vector space B can be written as a direct sum of irreducible subrepresentations. So D is equal to direct sum I. Yeah. Just break up like this. So, right, and this is, and just like what we had for G set, like a G set could be broken up into sort of a disjoint union of sort of transitive G sets. Every representation sort of under sort of these sort of conditions relating to characteristics of the field and the order of the group. We'll usually just work in characteristic 0 anyway, but I wanted to state sort of this in full generality. And so under these conditions, any representation sort of breaks up as a direct sum of the irreducible subrepresentations. Moreover, as we'll see, there's some uniqueness to the statement. The sort of, well, there's our isomorphism classes of irreducible representations. And there are isomorphism classes of irreducible representations, and sort of the multiplicity with which an isomorphism class sort of appears is unique, and mean, the way you break it up is not completely unique. If you have sort of a higher, more something appearing with multiplicity greater than 1, but anyway, it's unique in some sense. This decomposition. But good. And this says you can sort of break down representations in these elementary blocks in sort of the simplest way. Like there's not some extension structure here, like when we were studying how to build groups out of simple groups, and there's, or like sort of when you're doing sort of general module theory, like there's really just sort of this, you're just taking a direct sum of sub-representations. So of irreducible. So somehow like different irreducible representations aren't interacting at all. Yeah, I'll come back and prove that in a second. Let me sort of state the other important theorem. So Schur's lemma. If G is a finite group, and K is algebraically closed, you don't even, and G doesn't have to be a finite group here, but anyway, and V is an irreducible, a finite dimensional irrep of G, then the space of endomorphisms. So this is sort of, yeah. So this is just linear maps from itself that are sort of fixed by the G action. So in the sense we said before, saying a map from V to V is, so an element of GLV that sort of commutes with the action of G on V. Sorry, so this is equal to K cross. Sorry, the K. If I said automorphisms, then we get K cross. Okay, so these are the two most important structural statements about representations of finite groups. They decompose uniquely into irreducible representations. And then if you look at an irreducible representation, at least when K is algebraically closed, its endomorphisms are sort of just given by scalars. The second one doesn't look that strong, but like it organizes sort of a very powerful argument in sort of a nice way. Okay, so let's prove these real quick. We'll prove Schur's lemma anyway, and then we'll maybe prove the theorem just over the complex numbers. So proof of Schur's. So very simple. So suppose phi is contained in GV. Then, well, then phi has an eigenvalue. Lambda in K. Because, because K is algebraically closed. And so K is algebraically closed. And so if you look at the characteristic polynomial of phi, so the determinant of sort of phi minus lambda times the identity, well, that's a polynomial over an algebraically closed field, so it has a root. And that root is an eigenvalue sort of by definition. And then look at the kernel of phi minus lambda. So this is a non-zero, so minus lambda times identity. So the eigenspace for that eigenvalue. So this is a non-zero G invariant subspace. So, and the reason it's G invariant is because you're taking the kernel of some operator, and for the action, like the G action sort of commutes with its operator, because the G action commutes with multiplication by a scalar, and the G action commutes with this operator phi by definition. So that's how we chose phi. And so it preserves, and you can just write down the formula, but it preserves, the G action preserves the kernel. Okay, but the kernel is non-zero in G invariant subspace. So that means because V is irreducible, implies the kernel of this is equal to V. So then phi minus I, so phi, this operator phi minus lambda I times ID is sort of identically 0. So phi is just lambda times identity element. So phi is, with this element phi, which was sort of just an arbitrary element in here, we deduced that it had to be actually just sort of multiplication by this scalar lambda. And so that's exactly the statement, that sort of every endomorphism is given by multiplication by a scalar. If K was not algebraically closed, what you'd find, and you wouldn't find that this is not the answer you'd get, but what you'd find instead was that the endomorphism ring was always a division algebra. That could be a non-trivial division algebra. We won't use that though. Okay, so that's Schur's lemma. And then back to the proof of the theorem. And so this theorem is called complete reducibility. Okay, and I'm going to do it over the complex numbers. So, and then I will just remark about how you do it. And over the complex numbers is sort of a particularly simple proof. The same proof works over the real numbers. But then there's another almost as simple proof over any field. But somehow, when in fact, in the proof over any field is probably actually simpler, but somehow conceptually this feels easier because it's related to sort of an operation we're used to doing. Okay, let me say what it is. So let the, and so it suffices to say, it suffices to show that if sort of V is a finite dimensional representation, and then W containing V is a subrepresentation, then there exists a sort of W prime, a complementary subrepresentation of V. So a subspace such that W plus W prime is equal to V, and sort of W prime is a subspace. S is a subrepresentation. And once you have that, you just sort of proceed. You sort of just iterate this procedure to produce a decomposition to irreducible subrepresentations. So this is what you really need to show. So you just need to know whenever you have a subrepresentation, you have sort of a complementary subspace that is also a subrepresentation. So complementary subspace that is also preserved by the G action. So how do we do this? Well, suppose so V had a Hermitian inner product. All right, just brackets such that rho of G phi such that if I hit sort of V and W with the action of some element of G, and I sort of do the inner product, like I get the same thing. So another way to say this is the action of G is unitary. So the action of G sort of factors through the unitary group, which is the group sort of preserving this Hermitian inner product. But this is just saying, this is just a statement that the representation preserves this inner product. Well, then I claim that the perpendicular subspace the utility of having a Hermitian inner product is like it gives you a way to distinguish a subspace. Distinguish a complementary subspace. If you have some subspace, you can always just take the perpendicular subspace, and that's a complementary subspace. And it's easy to check that like when you have a Hermitian inner product that's preserved by this group action, then it will also, like this group action has to also preserve the complementary subspace. So let me not write that down, but you can check that on your own. So that means you're done if you have a Hermitian inner product that's preserved by G. Okay, so then how do you get such an inner product? Well, you take you just take any Hermitian inner product. So let me write with parentheses an arbitrary Hermitian inner product. And then you average it. You define our brackets inner product is going to be G invariant, just to be 1 over the size of G times, this constant doesn't matter, but because we're averaging, it's sort of nice to put it in. And then you sort of just take rho of G times V, this parentheses inner product of rho of G times V, rho of G times W, where you sum over all of the elements of G. So in this bracket inner products of the two things is the parentheses inner product sort of averaged over the whole sort of simultaneous orbit of V and W. And again, so it's really simple to check that this is it's sort of good. Yeah, it's simple to check that this is now preserved by G, and it's simple to check that it's still a Hermitian inner product. I mean, somehow like you won't have destroyed positivity or anything. Okay, and so that completes the proof. And you use an invariant inner product to produce complementary subspaces that are subrepresentations, and then sort of to get an invariant inner product, you just average any inner product. So it's sort of a nice argument. And the proof in general, and why did I work with the complex numbers for this proof? Well, so I had like a good notion of inner product that let me sort of take complementary subspaces. So over the like an Hermitian inner product gives you that over the complex numbers. Over the real numbers, I could have just taken a symmetric inner product. But like over the complex numbers, I couldn't have taken a symmetric inner product. I mean, like the orthogonal subspace for a symmetric inner product on in a sort of a non-degenerate symmetric bilinear form on the complex numbers, like sort of the perpendicular subspace might sort of not, like if I have a subspace W and I think it's perpendicular, like that might intersect W. So and the point is, there are very special conditions that let you have an inner product that sort of satisfies this sort of. And so whenever you have a non-degenerate bilinear pairing, like W perp is always going to have complementary dimension, but you need something special to guarantee that sort of a subspace doesn't intersect its perpendicular subspace. And sort of no such condition exists over an arbitrary field. I mean, you're using something special about the ordering on the real numbers in order to produce this positive definite property. And there's basically no hope of this argument as written above working. But I mean, if you look at this argument, we didn't really, and the inner product was just some tool. Like the inner product was just sort of some it was just some crutch that let us produce distinguished complements. But somehow, like, the key thing in this argument was not sort of this crutch for producing distinguished complements. It was the step where you sort of averaged to show you always had sort of a suitable crutch. And so what you can do is sort of, if you have an arbitrary k, you can take if W is invariant, then you can take W prime, a complementary subspace, and then sort of take the projection operator pi from. So when you take a complementary subspace, like, so that in particular means you have a projection operator. So you take pi from V to, so V is equal to W plus W prime. And well, you could write this other way. Let me write it as projecting onto W prime. So you just sort of project onto the second coordinate. And then yeah, and now just I want to average this projection operator. So now so I guess I should be slightly careful here. Okay, well, let me write it out, and then I'll figure out if I did something wrong. So I want to average this projection operator. I want to look at yeah, I'm going to look at sort of this, just the sum. So 1 over G. So I'm going to divide by G, and of course this is okay. So yeah, so let me take the projection onto W. Sorry. Sorry, that'll be better. So I'm going to use the sort of W as already G. So I sort of just take the natural action of G on sort of pi, which in pi is an endomorphism of V. And so this is, and I just average over the action. So this is literally sort of 1 over G, sum over G contained G. The action is you compose with okay, and you can, and well, sort of you can check, like, so let me call this sort of pi bar. Right, so bar stands for average. And pi bar of W is still going to be equal to W for sort of W containing W. Somehow just because pi sort of acted as the identity on W. And sort of the image of pi bar is still going to be contained in, well, that's by this first property, equal to W. So pi bar is a projection operator. And so it's a projection operator onto W. So it's a G invariant projection operator. And then, so then the kernel of pi bar is a sort of G invariant complementary subspace. So it's sort of complementary subspace that's also sub-representation. And so, and yeah, the only thing that we did for this proof was we released to prove it over an arbitrary K, well, sort of characteristic co-prime to the order of G, and that's because we had to sort of divide by the order of G here. Otherwise, sort of we wouldn't necessarily have a projection operator. Right, but okay, so and what we had to do is release our dependence on sort of this, sort of our traditional like undergraduate way of producing complementary subspaces using inner products, and instead sort of just observed like, I mean, somehow we didn't need like a uniform way to produce complementary subspaces anyway. Like, I mean, we're already going to sort of average to produce this inner product. And so we could just sort of take the arbitrariness at a different step. Like we could start, instead of taking sort of an arbitrary inner product, let's produce sort of an arbitrary complementary subspace, some complementary subspace. We could just take a complementary subspace, take the projection operator onto that, sort of corresponding to that, and then average that projection operator. And sort of this eliminates our dependence on having a reasonable notion of inner product. Okay, so let's stop there for today.